Good afternoon, Internet. I am Matt Buyak, and this is my third video in a series about prime numbers and working with prime numbers in C++. So in the last couple videos in this series, I mentioned that I intended this to have 3 parts. But in preparing for this video, I realized that there were at least 2 major topics that I still wanted to cover, and it didn't really make sense to put both of them in the same video. And so this will be the second to last video, and then the conclusion will be in the subsequent video. So in our last video, we put together this primes class for working with prime numbers. And at the end of that video, I mentioned that there was some work we still had left to do for our class to be a complete solution. And it turns out that that work is going to involve some pretty significant reorganization of our class. And anytime you're doing that kind of refactoring, that's a great opportunity for bugs to slip into your code. And so to prevent that from happening, you really want a solid set of tests to make sure you don't make any mistakes. And that's going to be the subject of this video. So as you recall, a few videos back, we put together this primestest.cpp, which has some basic sanity tests in it. And these are good enough to catch really egregious bugs that break everything. But if you have some more subtle bug that only affects certain values or only happens in certain circumstances, then this might not be enough to catch that. So when you're thinking about a more comprehensive approach to testing our class, what you might think of is starting from 1 and going all the way up to, say, the 10,000th prime, and checking to make sure that our class behaves correctly for all of those values. And so in preparation for that, I went online and found this list of the first 10,000 primes and added that to this header file here. And you can see we have our 10,000 primes ready for use in testing. So now if we go back to our class, you'll recall we have 2 main entry points here, this get prime and this other entry point is prime. And so it probably makes sense to write a corresponding function for each of those to test a single value with that entry point. And so that's going to be our approach. So we'll start with get prime. Okay, so we're going to have a function returns a bool to indicate success or failure. We'll say test get prime, and this is going to take let's see here, an index. We'll call it index, and the expected value. We'll also need to take our a pointer to our primes object. Okay, so let's also have a bool called result, and we'll initialize that to true. And then we'll calculate our prime from p. So we'll say uint32t, p is equal to p get prime index. And we'll say if p is not equal to our expected value, then we're going to print out some error message. We'll just say failure. Get prime was equal to this value, and we expected it to be this value. So we'll say index p and expected. And then we'll set result equal to false and return result. All right. And so our other function is going to have kind of the same layout. So let's just copy that. And so it's still going to return a bool. Now we're going to test is prime. And we will have a value n that we're testing for primality. And our expected value now is going to be a Boolean value. So we'll have bool expected there. Don't need this. And we'll just say if p is prime n is not equal to expected, then we say is prime equals, this has to change to %s, which I'll explain in just a moment, as does this. And so let's change some of these around. So this will be n. And so what does this %s mean, and what do we put for these two here? Well, it turns out there's no way to print a Boolean value in printf, and so we need to convert the Boolean value to a string in order to print it. And so we'll just write ourselves a little helper function here. We'll say static const character pointer bool to stir, and we'll say bool b, and then we'll say if b is true, then return true, else return false. Oops. Okay, so this is just taking a Boolean value and returning the corresponding string so that we can print it out. So then we'll just down here say, let's see. So we're going to print, bool to stir of our expected value, and then since it's a Boolean value, if we failed, then it's just going to be not, bool to stir not expected. So we saw the opposite of what we expected. And then we, again, set our result to false and return result. Okay, so now we have our two functions. Each tests one value with one entry point. And so let's clear out the tests that we do have. Those are just going to be redundant anyway. Let's see. So we'll need some indices for iterations. So we'll say I, j, probably need p to store a prime at some point. Yeah, I think that's probably a good place to start. So we'll say I is going to go from 0 up to 10,000. And we're going to check all the values for the first 10,000 primes. So first we might say, if was this test is prime primes data I, and we expect that that's going to be true. And if it's not successful, then we're going to, well, what we would want to do is say return 0, but then we're missing something here. You can see that we've got this, delete p, and we could very easily just accidentally return here and miss that we're not deleting our our primes object there. And there are a number of different ways to handle this situation, but I'm going to actually take the opportunity to introduce possibly the most reviled statement in programming, and that is the go-to statement. This is generally hated, and for the most part with good reason, but there are a few cases where using go-to makes sense. And one of them is if you fail out of a piece of code and you need to clean up, you need to do some kind of cleanup before you return. You put your cleanup code at the end, and then you can just jump down to your cleanup code. So we'll say go to end, and then down here we'll put end. And this is not the only strategy for dealing with this sort of problem of needing to fail out. Another way of doing it would be to wrap our primes pointer in a unique pointer or something like that, so it automatically gets deleted. But I think that's a subject for a different video. So this will be fine for now. Okay, so now we want to check that our prime not only is prime, but it's the prime that we expect. So we're going to say if not test get prime, and so it's going to be I, and the expected value is primes data I. Let's actually let's just say P equals primes data I, and then we can just do this like so. Okay, so if that test fails, then we're going to say go to end. But now we also need to test the composite numbers to make sure that they're behaving as expected also. And so we'll want to loop from the previous prime, or rather the number just after the previous prime, to our current prime. And so that's going to be j is equal to primes data I minus 1 plus 1, all the way up to j is less than our prime, plus j. Yeah, so then we'll want to say if not, let's see, test is prime j, and we expect that it's not prime, so we say false. And if our test fails, again, we say go to end. And you can see here how using this go-to statement is a concise way of handling this. And this actually brings up the other valid use case for go-to, is if you're in multiply nested loops, then using go-to to break out of multiple loops. So we have a statement, and actually we could have used this here. We can just say break, but here that wouldn't work. That would only break us out of this for loop. If we want to break out of both for loops, then we need go-to. And also, we actually, at the end of our test, want to print out something to make sure that everything's working. Like if we just get to the end of our test and it silently succeeds, then that doesn't exactly give us confidence. So we want to specifically print out like, yeah, we had success. And in that case, using break would not work, because then we would see success even if we had failed. And so go-to is still correct. Now we're still not actually covering 0 and 1 here. So excuse me, there's a couple mistakes here. So first of all, we can't do this check on I equals 0, and that's because there is no previous prime at that point. When our prime is 2, that is, and we want to check starting at the previous prime, there is no previous prime. And so we'll just say if I is greater than 0, then we're going to do those checks. But then, as I was mentioning, now we're not actually checking 0 and 1, and so we'll want to say, if not test is prime 0, false, go to end, and if not test is prime 1, false, go to end. Now there's still one mistake remaining in this code. Actually, it technically isn't in this code. It's in our primes class itself. Now, when we were first writing this class, it was to solve problem number 7, where we're asked to find the 10,001st prime number. And so it made sense. We just want to pass in 10,001 and get the 10,001st prime number. You'll see we're subtracting 1 here because arrays in C and C++, the first element is at index 0, not index 1. But this is kind of counterintuitive behavior, especially for someone who's used to working in C and C++. And in particular, if somebody were to pass in 0 here, we would read before the beginning of the array, which is definitely a bug and may even cause our program to crash. And so one easy way of fixing that is just to change our behavior here so that our list of primes starts at 0, or rather the index of our primes starts at 0. You'll notice that means now we also will match our test data, because if I go to primes data, you can see that the primes start at index 0, not at index 1. And so that's just a little bit of cleanup to better match what might be the expected behavior. Okay, so I think we're ready to run this and see if our test code works and confirms that our primes code works. So we build there. We appear to have some mistakes. Let me just too few arguments. Okay. So I've made the mistake of not passing in our primes object. So that should be just a real easy fix here. We just need to say P and P. So in reality, we would prefer to not have to do this. That is, what we would rather do is create our primes object inside these functions, because that better isolates our tests. So it's possible that one of these calls causes our class to be initialized correctly and the other one doesn't. But if we test, say, get prime first, it might hide mistakes in is prime or vice versa. And so to make those tests independent, we would rather create our primes object inside each of these tests. But if we try to do that, because right now, where our sieve size is 250,000, and we're testing all the way up to, if we check our primes data, all the way up to 104,000. So just to get a ballpark of what we're talking about here, that's on the order of 26 billion operations. And so that's really not going to be feasible if we're initializing our primes object for every individual test. And so for now, we'll just have to be content with having our primes object initialized once and used across all of the tests. Also, I need to actually include our primes data.h. And we have success. Wonderful. So this gives us some pretty good confidence that our primes code is currently working correctly. That means that in the next video, we can go into making those final changes to complete our solution for working with prime numbers here in our primes class. And you can look forward to seeing that in the next, and I very much hope, final video in my series on primes in C++.